Hello students, last time we have studied the rigid diatomic molecule and its rotation about a bond axis. Then we also studied about the rotational spectra of rigid diatomic molecule, and we have derived the equation for vibrational energy of a diatomic molecule. Now today in this particular lecture, I'm going to further explain the vibrational energy levels of a diatomic molecule. Then we are going to study about the vibrational spectra and vibrational rotational energy level of diatomic molecule. And finally, a very important phenomena related to molecular spectroscopy, which is known as fluorescence. This phenomena also we are going to study here in this particular lecture. After studying these topics, students will understand vibrational energy levels of diatomic molecule. Students will also understand the vibrational spectra and vibrational rotational energy level, and you will learn about what is fluorescence and what are its applications. So let us start with the vibrational energy level. If you remember, last time we have considered the diatomic molecule, and if you assume the vibrations of the atoms about their mean position, and considering this vibration, you can convert this diatomic molecule or a two particle system in a single particle system, so which is fixed at certain end and attached a reduced mass is attached with a spring. So a spring which is representing the force between the two constituent atoms in the molecule. So you can replace a two particle system into a single particle system, and this can be considered as a simple harmonic oscillator. So by solution of this simple harmonic problem by Schrodinger's equation, we can obtain the equation of the vibrational energy levels of diatomic molecule. And last time we have seen this equation. So the vibrational energy of a diatomic molecule EV, that is equal to V plus half into h nu 0, where nu 0 is the classical frequency of oscillation, or you can say the natural frequency of oscillation of this diatomic molecule, and it is given by nu 0 is equal to 1 over 2 pi under root of k upon m dash. K is a force constant which represent the bonding force between the two atoms, and m dash is the reduced mass. So you can convert the two body system into a single body system having a reduced mass m dash. M dash is equal to m1 m2 upon m1 plus m2. We have seen this reduced mass also. And here V is the vibrational quantum number. So you can see here this vibrational energy of a diatomic molecule is also quantized. It cannot take any possible value, but there are only certain discrete values allowed, and this discreteness of vibrational energy that that is defined by this quantum number, which is known as a vibrational quantum number, and let us represent it by V. So we can take the values 0, 1, 2, 3, and so on. So the energy, vibrational energy of a diatomic molecule is also quantized. Now if you consider V is equal to 0 in this particular equation, so that the energy we can represent as the lowest energy, or we can also call it as the ground state energy of this diatomic molecule. And this ground state energy, by substituting V is equal to 0 here, so let us use the suffix 0 to represent the ground state energy. So E0, that is equal to, this is 0, so 1 half h nu 0, and nu 0 is this classical frequency which is represented by this equation. Okay, so this is the ground state energy of the diatomic molecule, vibrational ground state energy of diatomic molecule. Now, from this equation, one can draw the vibrational energy levels. So, on the left hand side, you can see the vibrational quantum number. V is equal to 0, 1, 2, 3, and so on. So, these are the vibrational quantum number. And the corresponding energies they are represented. So you can calculate these energies by using the equation E0 is equal to V plus half. So inside the bracket V plus half into H nu 0. So if you substitute V is equal to 0, as we have seen, E0, the ground state energy, that is equal to 1 half H nu 0. If you substitute in the earlier equation, so in the earlier equation means this equation, okay? If you substitute V is equal to 1 here, so 1 plus 1 half, that is 3 by 2 H nu 0. So that is what we have represented here. So for V is equal to 1, E0 is equal to 3 by 2 H nu 0. Similarly, V is equal to 2. So substitute V is equal to 2. So 2 plus half, that is 5 by 2. So E0 is equal to 5 by 2 H nu 0. Sorry, so you should represent this as E1, E2, E3, not E0 everywhere. Okay. So you should correct this one. Okay. So this is E0, E1, E2, E3 and so on. So these are the energies of the corresponding levels represented by the vibrational quantum numbers. So 3 by 2, that is V is equal to 1, 5 by 2 H nu 0 for V is equal to 2, and 7 by 2 H nu 0 for V is equal to 3 and so on. Okay, so you can just draw a vibrational energy level of a diatomic molecule. So what you can see here is these energy levels, they are equally spaced. So if you consider any two adjacent energy levels, so you'll find that there is an energy difference of delta E is equal to H nu 0. For example, this E1 and E0. So E1 is 3 by 2 H nu 0 and E0 is 1 half H nu 0. So 3 by 2 minus 1 half, that is 1 into H nu 0, that is H nu 0. So everywhere you will find that the difference is same. That means you can say that the energy levels are equally spaced. Vibrational energy levels are equally spaced. Then one more important difference you can see here, if you recall the study of rotational energy levels. So at that time we have seen that for the rotational quantum number 0, the ground state energy was also 0. Rotational ground state energy of diatomic molecule, rigid diatomic molecule, we have seen that it was 0. But here the vibrational energy for the ground state of a diatomic molecule E0 is non-zero. Okay, so the energy of ground state is non-zero, and you can see further the energy levels are quantized here. So these are the main features you can see about the vibrational energy levels of a diatomic molecule. Now considering the different levels, for example, E0, we have seen that is equal to 1 half H nu 0 and E1 is equal to 3 by 2 H nu 0. So therefore, if you consider a energy difference E1 minus E0, that is H nu 0. Similarly, E2 minus E1, that is also H nu 0. E3 minus E2, that is also H nu 0. So any two adjacent levels, you will find that the energy difference is same, and that is equal to H nu 0. So you can say the vibrational energy levels are equally spaced with energy interval of H nu 0. Now, if you want to discuss or if you want to know about the vibrational spectra, so whenever there is a transition among these levels, energy levels, that will result emission of the photon of energy, which is equal to difference between the two energy states where the transition has took place. Okay, so that is decided quantum mechanically again. So there is a strict rule, which is a selection rule for transition between the vibrational energy level, and it is given by delta V is equal to plus or minus 1. Delta V represent the difference between the two values of vibrational quantum number, that is V. So for those two levels where the difference is either plus or minus 1, only for those levels the transitions are allowed. That means the transition among the adjacent levels are only allowed because there is a difference of quantum number, vibrational quantum number, that is equal to plus or minus 1. And thus any other transition for which the difference in quantum numbers is greater than 1, plus 1 or minus 1, these transitions will not be allowed, remember. So therefore this selection rule is followed in the transitions, and whenever such transition took place, the difference of the energy, that is equal to h nu 0, is given in the form of a photon, which constitute the vibrational spectra of the particular molecule. So the if you consider this oscillating dipole, any diatomic molecule, you can consider it as an oscillating dipole whose frequency is nu 0. So classically its frequency is nu 0. Therefore, it can absorb or emit radiation of the same frequency, and that is what the h nu 0 here, energy interval that is equal to h nu 0. So remember here, the vibrations of a molecule, it can be visualized as oscillating dipole, and therefore its frequency is classical frequency is nu 0, with which only it can absorb or emit radiation. Now, if transition occurs, let us consider a simple theoretical example, or you can say explanation. So, if a transition occurs from energy level with quantum number V plus 1, so higher energy state represented by quantum number, vibrational quantum number V plus 1, to an energy level with adjacent and lower state, that is represented by quantum number V. So one of the state having quantum number V and higher state has its vibrational quantum number V plus 1. So if you consider the transition between these two levels, then you will be able to find out the difference. So according to the quantum mechanical concepts, delta E is equal to h nu. So h nu is equal to delta E, and that is equal to the difference between these two levels having quantum number V plus 1 and V. So E V plus 1 minus EV, that is equal to, you can now represent the energy here with the help of the formula. So V plus 1, this is the vibrational quantum number, plus 1 half into h nu 0. Similarly, minus the quantum number here is simply V. So V plus 1 half, actually here it should be 1 half into h nu 0. Okay, so this particular case, h nu 0 will be, so if you take this common h nu 0, so this will get cancelled. This should be actually 1 half, remember here. So it should be V plus half and V plus half, and this one of the h nu, it will remain here, h nu 0. So everything will cancel except h nu 0. So h nu is equal to h nu 0, or you can say simply h will cancel, nu is equal to nu 0. Okay, so nu is equal to nu 0, what does it indicate? That the frequency of the photon given out, it is same as the classical frequency of the oscillating dipole or the diatomic molecule. So nu is equal to nu 0, it has the significance. But nu 0, as we have seen, the classical frequency is given by 1 upon 2 pi into under root of k upon m dash, where m dash is the reduced mass. So thus, from this relation, you can say nu is equal to nu 0, that is equal to also 1 upon 2 pi under root of k upon m dash. So thus, the frequency of radiation emitted or absorbed is equal to the classical frequency nu 0, irrespective of the value of vibrational quantum number. So whatever the value of vibrational quantum number, okay, V plus 1. So V can be any value here. Its adjacent value is V. Okay, therefore whatever the value of the vibrational quantum number, irrespective of this value of vibrational quantum number, the frequency of radiation emitted or absorbed is same as its classical frequency nu 0. So nu is equal to nu 0. It has the same meaning. Therefore, the vibrational spectra lies in the infrared region. Okay. So for the oscillating dipole, that means the vibrations performed by diatomic molecule, the vibration spectra lies in infrared region. And this infrared region, it ranges from 8,000 angstrom unit to almost 50,000 angstrom unit. So this is the range of the lines observed in vibration spectra for different molecules. Okay, now let us discuss more about the vibrational rotational energy levels of diatomic molecule. Okay, so vibrational rotational energy levels means what? Let us try to understand. Okay, so you can see this is the energy axis. As earlier also we have discussed about the potential energy varying against the intermolecular distance of a diatomic molecule. Now, this is on energy axis, this is the minimum energy. So you can say that this is the ground state. where the atom, sorry, the molecule is most stable because it is having the minimum energy. And these are the excited levels, you can say. So this is V0. V0, you can say vibrational level, and it is the minimum energy level, ground state energy, and here you can say the molecule is most stable. So the vibrational energy level V0, V1, V2, V3, V4, and so on. Okay, they are represented by this horizontal line, and in between you can see the small bundle of lines. These are actually rotational levels. So earlier, while studying the type of spectra, molecular spectra, we have seen that there are three types. Okay, rotational spectra, then rotational vibrational spectra, and electronic spectra. So rotational spectra has the lowest energy. So and the vibrational energy levels, they are having slightly higher energy than the rotational energies. Therefore, you can see in between two vibrational states, there can be number of rotational energy states also. These are represented by the horizontal line. Okay, now if you see the shape of this potential energy curve, this is the minimum energy. And as you increase the distance, intermolecular distance, here the initial parabolic nature of this curve, it extends far away, far away. So the parabolic approximation, if you consider in this particular region, there is, you can say there is a parabolic approximation. It is very much same as that of the energy at the minimum point. Okay, but later on, as the value of vibrational quantum number increases, this nature, it deviates from the parabolic approximation. So what is the reason here? As we have seen earlier, the vibrational energy level, they are equally spaced, but practically at high value of V, vibrational state do not obey the relation. That means this relation is not true for higher value of V. So this is because of the intermolecular distance. The separation increases and the actual curve deviates from the parabolic nature. So this is a parabolic approximation. And therefore here the equation will be no longer satisfied by the higher value of V, and therefore the energy values go on decreasing as the V value increases. So you can see the separation among these vibrational levels, as V increases, the separation goes on decreasing. Okay, the separation goes on decreasing. So this is a very important fact about the vibrational energy levels and the rotational levels. You can see in between, they are also shown over here. Okay, now the some of the important facts we shall now discuss about the vibrational rotational spectra. So pure vibrational spectra. Now pure vibrational spectra means what? The atoms in a molecule are only vibrating, they are not rotating, and the electron from the constituent atom, they are also not excited. That means the electronic configuration is same. So such state, you can say it as a pure vibrational spectra. But pure vibrational spectra is observed only in liquids where interaction between adjacent molecules inhibit rotation. So you know that in molecules there are the intermolecular forces in liquids. Okay, in case of liquid molecules there are intermolecular forces, and because of these forces the rotational motion is inhibited. What is possible is only the vibrations of the atoms, constituent atom in the molecule. So only pure vibrational spectra can be observed for the, you can say, liquids only. But if you consider the gas or vapor, then the molecules are free. So along with their vibrational state, they can also perform rotations. They can also perform rotation. So what will happen in this particular case? Vibrational state and rotational state, they are parallelly present at the same time. So vibrational levels and rotational levels, they can be represented in the same diagram as we have shown here. Okay, these are the vibrational levels. So for gas or vapor, you can see the vibrational states are also possible and rotational of molecules are also possible. There are some rotational levels also. Okay. So because of this, what happens here? So spectra of such molecule means either for gas or vapor, spectra of such molecule consist of closely spaced lines which appears as a broad streak called a vibrational rotation band. So the if you consider any two adjacent vibrational lines of such or vibrational energy levels, energy states, and in between these the molecule has certain number of rotational levels also which fall in between the energies of the two vibrational levels, and whenever there are transition among these lines according to the selection rule, the spectral lines will appear. So the spectra of such molecule consist of closely spaced line because of the very large number of rotational lines or levels they appear in between the vibrational levels. So such a spectra appears as a broad streak and therefore it is called as a vibrational rotational band. Now all type of molecules exhibit electronic spectra. Remember, so pure vibrational spectra is represented by liquids only. Okay, uh, pure vibrational spectra represented by liquids only. Whereas in case of gas, it can be a vibrational rotational spectra. But the electronic spectra parallelly can be also shown by this molecule. So all types of molecules they exhibit electronic spectra, either gas, solid or liquid. All these they can show the electronic spectra. So in electronic spectra, you know that energy involved is quite large as compared to the rotational spectra or vibrational spectra. And the transition of the electron, okay, so from its ground state to excited state and back again to the ground state, that will result into emission of certain amount of energy in the form of photons that will constitute certain characteristic wavelength to form a spectra of that particular element. Okay, now the molecules, homonuclear molecules, especially like hydrogen molecule, nitrogen molecule, which have neither rotational nor vibrational spectra. So these types of homonuclear molecule, earlier while studying rotational spectra, we have seen that they do not show such a rotational spectra, and they also not show the vibrational spectra because of the symmetry of the molecules. The oscillating dipoles, they cancel out the actual effect of each other. So therefore, the vibrational spectra and the rotational spectra is not possessed by this homonuclear molecule, but they can show the electronic spectra. They only possess the electronic spectra. Okay, now let us come to the next point here. A very important effect which is observed in case of uh, molecules. So in molecular spectroscopy, this is a very important effect known as fluorescence. Now, whenever a molecule is excited from a ground state to the higher state, then it will come back to its ground state. But this transition can be performed in different way. So how? It can be performed by two ways. First is it may emit a photon of same frequency as that of the photon it has absorbed and come to ground state in single state. So what will happen? From excited state, it will come down to ground state by giving out the photon having energy that is equal to difference of these two states. So therefore, this is resulting in emission of certain photon or absorption of certain photon in case of absorption spectra. So this is the first single step method. But another method where the molecule may give up some of its vibrational energy in collision with other molecules. That means the molecule will perform collision with its adjacent molecule and thereby losing some small, very small amount of energy. So this loss is actually radiationless loss, we can say that. And so that the downward relative transition originates from lower vibrational level. Okay. So whatever the level to which earlier it has been excited, So what is expected theoretically? From the same level, the molecule should have performed reverse transition. That means from excited state to ground state. But this is not happening. Why? Because when it goes to the excited state, it is performing collisions with some adjacent molecules and losing some small amount of energy. So it will come down to some other lower vibrational level in the excited state, and then it will perform the transition. So definitely in such case, the transition, the emitted radiation has lower frequency than the absorbed radiation. So the actual energy difference will be lower as compared to the excitation, the point of excitation. And therefore, the energy given out in this particular case, that means a photon having energy less than the energy used in excitation or energy absorbed. So this effect is known as the fluorescence effect. This effect is known as the fluorescence effect. So this is shown over here in this energy diagram. You can see here. You can visualize this as the ground state of a molecule, and this is the excited state of the molecule. Okay. So we have certain vibrational levels in the ground state, and we have certain vibrational levels, energy levels, in an excited state. So suppose the molecule is excited from its ground state to excited state. So from this vibrational level to this particular vibrational level. Now what happens? It performs collision with some other molecules and lose some small amount of energy. You can see small arrows performing reverse transition from the higher vibrational energy to lower, and again here. So these are radiation less losses because the energies involved here are less, and therefore now when certain number of particular transition it has performed because of the collisions with other molecule, now it will come back to the ground state, but it will not come back from the same vibrational level where it has reached from the ground state. What we expect theoretically, it should have perform a reverse transition from this level to this level, but this is not happening. This transition took place from this level. Okay, it is slightly having lower energy than the earlier, and it will perform a transition up to this level. So this energy and this energy, definitely this energy is less, therefore the photon of less energy will be given out. That means the photon of less frequency will be given out, and this phenomena is called as a fluorescence. This is called as a fluorescence. So this fluorescence has number of applications. Few applications just we shall discuss here. This phenomena of fluorescence, it can be used to identify minerals and some biochemical compounds. Then a very simple application of this fluorescence is these kind of materials, they are used in fabric brighteners. So what is the role of these fabric brighteners? They are present in the detergent, and they will add UV radiations from the sun, and they will go into excited state, and thereby losing some amount of energy in the radiationless losses, and come back again to ground state energy. But they are giving lower energy. Lower energy means what? UV has higher energy, lower energy. So lower energy radiations as compared to UV are visible. So they are giving the radiations in the blue region. So the fabric will appear as if it is very bright. So they are functioning as a fabric brighteners. Then a simple example of fluorescent lamp. Fluorescent lamp, everybody you know that fluorescent tube where we have mixture of mercury vapor and inert gas like argon. So what happens here actually, because of the electric arc at the two filaments inside a tube, these mercury molecules, the mercury and argon, these particular inert molecules gas are present here in the mercury vapor. So this mercury molecule will go into excited state, and they will perform some radiation less losses and come back again to ground state. They are giving, actually the mercury vapor when it go to excited state and perform transition, they will give out UV radiations. But these UV radiations, they are actually absorbed by a fluorescent material which is coated from inside on the tube, just like phosphor. And this phosphor, even though it absorbs UV radiation, higher energy, but because of fluorescence effect, it gives out the blue light in visible region. So this is a simple application of the what we call as the fluorescence phenomena. So these are simple applications of the fluorescence phenomena in different fields.